All right, good morning, everyone. So, quick note about quiz 1 that is coming up, soon, next week. So you'll see that the other section is kind of behind us in some ways, and we're behind them in other ways. Don't worry about it. We'll look at the quiz stuff together, and anything that both sections haven't covered, we'll just throw out. So we're all good. And like, for example, the other section doesn't know how to make processes yet. They haven't gotten to that fun fork, orphan, zombie discussion yet. So that's the hardest part of the course. So we essentially front-loaded everything. The hardest part of the course is already over. Not really. And then, yeah, I guess that's it. So quiz 1, 2 will be mostly like multiple choice, true, false, like 80% of it. And then the other 20% of it will be like, here, explain something, right? So it shouldn't be too bad. It's only going to be an hour, so for better or worse, it'll all be over soon. All right, so today we're going to be talking about IPC. We can kind of relax and just learn for a little bit. None of this will be on quiz 1 because the other section won't cover it, but it's just kind of important just to help us understand what's going on. There's some things at the end of this lecture that they have covered that I'll point out that is valid for quiz 1, but for like the first half of this course, we can just kind of relax and enjoy the ride that is IPC, or inter-process communication. Because remember, if we have processes, they're completely independent from each other. One doesn't affect the other. Even if we change what looks like the same memory address, they're completely independent. It doesn't affect the other one. While in a lot of scenarios, if we want to do something useful, we actually have to communicate between two processes, and the mechanism for that is called IPC, which stands for inter-process communication, just a fancy way of saying communicating between two processes. So any communication between two processes, since by default everything is isolated, it has to be explicit and then therefore explicitly allowed by the kernel, right? You want to make sure processes are talking to other processes that they should be talking to. So you can think of IPC at the most basic level as just transferring bytes between two processes. And I mean, in computing, we're just transferring numbers between each other and just giving meaning to them just because we want to, right? At the most basic level, that's all computing is. So reading and writing files is even a form of IPC, which you've all done before, right? So if you have a process that opens a file, writes to it, that would create a process. That process writes to a file. And then later on, if another process reads from the file, that's actually communicating between two processes that aren't even alive at the same time. So another process comes, reads from that file, and that's how you get bytes from process A to process B, right? And that's all done through the read and write system calls. And they just allow any bytes, they don't care. So the simplest thing we could write, or one of the things we could write, is a process that writes everything it reads. Because remember, we have these standard file descriptors. So standard input is file descriptor 0. Standard output is file descriptor 1. So we could read from standard input, which is just by convention, file descriptor 0. And then we could write to standard output, which is, again, by convention, file descriptor 1. And let's go ahead and just see that, and we'll see if it reminds us of any program we've seen before. So here is our program, read write. So in our program, we just declare a buffer of size 4096. This number will be important to you later on when we get to memory management, but for now we can just say, hey, it's a kind of big buffer. So the read system call takes a file descriptor, a pointer to a bunch of bytes that you want to, that can store some bytes that the kernel writes for you, and then you have to say the size of it. So we give them a pointer of approximately 4,000 bytes and say, hey, you can write up to 4,000 bytes. So this is in a while loop that just continuously calls it while it has some bytes read. So the return value of read, it returns the number of bytes read. So if it's greater than 0, it's read some bytes, and we'll have to read more if we want to get all the bytes of that file descriptor. So after we read some bytes, we go ahead and write to file descriptor 0 using that same buffer and just writing out the number of bytes we have read in. And it will also return the number of bytes written because the kernel doesn't really care about you too much. Your write system call is merely a suggestion. It can write 0 bytes if it wants to and asks you to retry. Or it just might do partial writes, and then you have to deal with the consequences at the end of that. But it's a standard C function, so if there is an error, it returns -1, sets error no, so we just print out our error. And in this case, I said that it might not write everything, so I want to be lazy, but also be kind of defensive. So I'm just going to assume that it always writes out the number of bytes I've read in before, so it just outputs the whole buffer. And I don't want to be caught by surprise, so I just put an assert there that if it does partial reads or anything weird, I'm just notified of it instead of like doing what Java likes to do and kind of failing silently and being impossible to debug. And then at the end of this, right, so the while loop will go through again while read is greater than 0. Then there's 2 options to break out of this while loop. One being if there is an error in read, in which case, it would return -1. And we assert that the only other value at this point, if it's not an error and it breaks out of that loop, this is just a sanity check, mostly for documentation, because this should never trigger, is that the bytes read is 0. And you'll notice that there's no like end of file or anything. We could read an end of file. There's no end of file character or anything special. The only way you know you've reached the end of the file is if read returns 0. Like I'm out of bytes, it's done. I don't have to read anymore. So let's go ahead and execute that. So it's just sitting here, right? The first thing it needs to do is read. And reading from standard input, which by default, if I just type something on my terminal, it's just waiting for terminal input. So I could do something like this, and then if I hit enter, what does anyone expect to happen here? Yeah. Yeah. So it should output hi, hi, hi back, and anything I type here should just echo it over and over again until I hit, on Unix, if you want to like close the open file descriptor in your terminal, you hit Control D, and that means end of file. So read would have returned 0, and then it goes ahead and exits the process. So does that remind us of anything we've seen before, might have used if we've used a bunch of Linux stuff before? Yeah. Echo, wait, is that what echo does? No, nope. Any other little programs we've used? If you want to display the contents of the file on your terminal, what? VIM. Sorry? VIM. Yeah, so we could use cat. That's another way to do it, but that's like a full-blown text editor. But I could use cat, right? If I use cat and do it, it looks exactly the same. And I hit Control D and it ends. So what we just wrote is actually cat. So cat's not that complicated. It's like, but we'll see soon it's actually kind of powerful to have that. You've been using it, and I mean, how many lines did it take us to write it? Like, even error checking, it took us like 19 lines. If that, there's like header files up there, so it didn't even take 19 lines. So that's the entire implementation of cat. Cat would do something smarter if there's like a partial write there, right? It would retry the write, but that's just another while loop. Oh, we've written cat. That's kind of cool. Yeah.
So for write, how do we decide it's overwrite or just append character at the end?
Sorry?
Like for write, how do we determine it's overwrite or just append the character at the end?
So write will just always just keep on appending stuff by default.
Is there any way that we can overwrite the
Yes. Yeah, so the question is, with the write, does it just always append if the file descriptor happened to represent a file, or can we go backwards and overwrite things? The answer to that is we can go backwards to overwrite stuff, but we won't see that till later. But the default behavior is just to keep on appending bytes to the end. Yeah.
If in the byte buffer, like you want to write 4,000 bytes,
Mm-hmm.
in a byte buffer you have a terminal, the /0 at say 1,000 byte.
Yeah.
Would that keep writing the rest of the 3,000?
Yeah, so the question is, whoops, if in our buffer there happens to be a null byte somewhere, does that stop writing? And the answer to that is no, the kernel doesn't care. It's just a bunch of bytes. If it stopped at the null bytes, you suddenly wouldn't be able to write 0 to any file, which would be really, really weird. The kernel doesn't care. A null terminated string is just a C convention. The kernel does not care whatsoever about it. So you can write anything, including the null character. It'll just keep on going. It'll write as many bytes as you ask it to, no matter what the byte is. Okay. So let's extend this a bit. So here's just for your reference, read just reads from a file descriptor. And if it returns 0, it means there's no more data to read from that file descriptor is essentially done with. And you could go ahead and close it or just ignore it, whatever you want to do. But you should always check for errors too, like especially for write. It's kind of weird because we now know printf calls write, and it might not ever write the bytes. Printf actually has the same return type where it tells you the number of bytes it's written, but who's ever checked the return value of printf? Right? One person. All right, one person's checked the return value of printf. But we just kind of assume it works because for the most part, if it's under 4,000, that 4,096 bytes, it'll always work for the most part. Yeah, the write just returns the number of bytes written. You shouldn't assume it's always successful. We'll see. Actually, we won't see that, but you shouldn't assume it's always successful. But I guess for the purposes of this course, if they're small, you can assume it's successful. But always program defensively, put some asserts that, so if you're not right, you actually know what happens and can actually fix the problem. So, and of course, communication's a two-way channel, right? In our process, we read from standard in and then write to standard out. Well, something was communicating all the bytes I typed in to my process. So there had to be some corresponding thing on the other side of that file descriptor. So whatever file descriptor 0 was in my process, someone called write to write some bytes to it that I could read in my program. And then consequently, when I wrote some bytes out, another process had to read the bytes out so it could display what I just wrote, right? And that's kind of a powerful concept we'll see as we go on. So yeah, and there's a reason for doing the standard file descriptors as opposed to just confusing you relentlessly. So what we could do as a little trick is we could close standard input, right? There's a close system call that just takes a file descriptor that closes up a file descriptor so we can't use it anymore. So we could close file descriptor 0, that would free it up, and open a file instead, right? In lab 1, you had to do that open system call that returned a file descriptor. So Linux and other Unix systems just will use the lowest available free file descriptor for new ones. So by default, you'll have like 0, 1, and 2 open. So if you open just a new file, it'd get file descriptor 3. But if you close file descriptor 1 and then open a file, that file will be file descriptor 0. So let's see what happens when we change that. So we're going to keep the exact same core loop we had before, and we're only going to add a open call. So here we just check that there are at least 2 arguments, and if there is, if there are exactly 2 arguments, we take the argument as a file, we open it as read-only, and then open will give us a file descriptor. And in this case, since we closed 0, it would get assigned file descriptor 0. And then otherwise, we'd have the exact same program as before. So without changing anything, it's now going to read from a file instead of read from my terminal, right? If I be meta and do openExample and openExample.c, read now instead of reading from the terminal should be reading from that file. And again, we didn't change where it's writing to, so it should just appear on my terminal, right? So it does so that's the contents of the file. It's now on my terminal. And that's the exact same thing that would happen if we catted that. So we were missing some functionality of cat, but now we have it. So we've written a full cat program now, right? And we didn't actually have to change the core logic here, right? We just read from descriptor 0, and we wrote to file descriptor 1. And by changing what file descriptor 0 was, we can support lots of different things. So now we can support a terminal, we can support files, and all that great stuff. All right, any questions about that? Kind of cool. Well, I didn't actually have to, I could have just kept my read-write example. If you're using like bash or something like that, bash allows you to change where file descriptors go and will open files for you. So you can support files without ever having to write any open system calls or any file handler code whatsoever. So in this example, this could be read-write example because I don't give it any arguments. You can use this character on your terminal, and it will essentially replace file descriptor 0, which is why it points into the process. So you can think of it as changing standard input with openExample.c. So your terminal itself will open that file for you and then feed it into that program. So even if I do the read-write example that doesn't have an open system call whatsoever, and I feed that file into it, I get that file right back out, right? Okay, we don't want to do that. So I get that file right back out. So the way standard file descriptors work is, hey, your programs can, even if your program doesn't support files, through kind of just modifying what file descriptors point to, you can have it support files without the process itself actually having to support files. So you didn't actually have to write that system or that open. We just kind of wasted our time. Other fun things you can do is there is this pipe character that essentially takes a process on the left and connects its standard output to the process on the right. So anything that comes out of cat openExample, which would normally go to file descriptor 0, right, standard output, which would just dump the contents of a file, instead of going to your terminal, it would go to this process as standard input. So let's see that. So if we just cat openExample.c, we get the normal file. Otherwise, we could cat it to openExample, or we could just pipe it to openExample.c, and it should just pass into our program, and then we would write it back out again. So this is kind of a roundabout way to do that. And you could also link them together. So our program was essentially cat without arguments, so I could do this as many times as I want because cat just, reads in everything it writes out everything it reads in. So I could connect, this just connects the two processes on either side. So I could connect them as long as I want, and I'll get the same output again. So you could, of course, do something much better than that. So the other way, so if there's an arrow going to the left, you can also have an arrow going to the right. So what you could also do, if I cat, openExample.c, by default, it'll just go on to my terminal because that's what standard out is connected to. But if I use this arrow, so if the left arrow goes to standard in, the right arrow goes to standard out. So I can make it write to files without having any file handler code. So I could say output.txt, and then that would take that openExample.c, redirect it to a file called output.txt, Now if I look at output.txt, it's going to have the exact same contents, right? And also, what does this actually remind you of? Yeah. Yeah, so because of the Unix philosophy of having all these file descriptors, you actually don't need a CP command. You can just use cat and redirect stuff. So copy is mostly just for your convenience. Otherwise, all you really need is cat, which is a dead simple program, just writes out everything it reads in. And hey, you can copy files. You can do all sorts of fun stuff. Yeah.
Could you explain again what that means, redirect across multiple processes?
That pipe character? Yeah, so it just connects this process's standard output to this process's standard input.
So it will execute the .c file and put the input to the executable.
Yeah, so if I just run this example.c, it'll just show the contents of the file on my terminal. If I instead do that pipe character, it'll feed that contents to this process, which unfortunately just does the exact same thing, but instead of going directly from this process to the terminal, it goes from this process to this process, and then this process outputs it to the terminal.
Yeah, that makes sense.
Yep. Yep.
Why did we have to add to check the file descriptor with -1 to make it fully?
Yeah, that's just error checking code. Yeah, so it's like a standard C wrapper. So if it returns -1, there's an error, and it sets error no.
And error no is just.
So
You didn't define that in the code before. That's just a standard.
yeah, so that's just a standard thing that C sets for you. For now, until we learn about threads, think of it as a global variable. So it's a global variable that C controls for you. Yeah.
So you always read the file from the file descriptor 0, so you're always assuming the first file input will be on the file descriptor 0.
Yeah, and that's just the convention. That's just the Unix convention. So
Is it always guaranteed with other process disturb that? So other process make other file descriptor.
yeah, so the question is it always guaranteed that 0 is like valid and can read? And no, it's just a convention. Thankfully, everyone follows it because your programs work, but it doesn't have to be. It's literally just a convention that everyone agrees to follow. Yeah.
If you close at the beginning of your program, close 0, open up another file, and that takes the place of 0, and then you scanf it, go read that file.
Yep. Yeah. Scanf just reads. It does the same thing. It just reads from the standard input. So since we know more about operating systems, you can change the standard input yourself. And similarly, I could close file descriptor 0, open a file, and then my printfs instead would go to that file. Yeah.
In the demo, you just showed you try to append a lot of cat at the end of this command.
Yep.
So what does that mean? Like just to pass the information to the back?
Yeah, it just keeps on going. VM. So like this. So instead of just, before it just took this output, provided it to here, and cat just reads everything it runs in, right? So this output is going to go into the input of this, which is going to output the same thing, which is going to go to this, which is going to output the same thing, which is going to go to this, and keep on.
Is the FT part the terminal?
Sorry?
So the output of open example will go to on the right. Is that's blank? Is that terminal?
Here, blank, like
Yes.
the space doesn't mean anything.
So where does the output go?
So the output of this would go into this process, this cat.
That cat goes to on the right.
Yeah, and then the output of this cat would go to this one.
And that's blank. That's.
And then the output of this cat goes to this one.
Then on the very.
Then the output of this, we're not changing file descriptor 0 or 1 on this case, and by default, it's still the terminal. So this one would actually print to the terminal, which is why I see something at the very end. Okay, yeah.
For this example, can you scroll up?
In the code?
Yeah, so if you open if you open two files, if you have fd1, fd2, and then you close the file descriptor 0, which file is it gonna write system error?
So file descriptors are unique. So if I open two files, one's going to get file descriptor. In this case, one would get file descriptor 0, the other one would get file descriptor 3.
So the first one is gonna get file descriptor 0.
Yeah.
Okay. So the one you open first will be output to standard out.
Yeah. Yeah, and also, so the question about the conventions of files, hey, well, is file descriptor 0 always valid? Well, now it's not. So someone else could do this to you, just close 0 and then start your process. So if I do that, what is it? If I do open example, give it an argument, and I try and read it, it says bad file descriptor. So good thing I checked my errors. So someone could have done this to you, and then suddenly your process runs, your file descriptor 0 is not valid, and you can't do anything because it's not valid. So this could actually happen to you. So always good to check your errors. But if that happens, someone not you has not followed conventions, and something horrible has happened. Okay, so this is kind of the more important thing. It's signals, which you can think of as interrupts, but they're interrupts for user mode. So everyone's seen interrupts and kind of used them before. So has anyone ever, when they run a program, hit Control-C? We've all hit Control-C. How many times, has it ever happened when you hit Control-C that the process doesn't end? Does anyone know why that is? Yeah. Okay, so they're free to ignore it. So signals are a form of IPC, and again, you can think of them as interrupts for user level programs. So what you saw in your other course, when you did interrupts at a hardware level, the kernel would have to do that, and we'll see some details of what the kernel's job of handling those interrupts are, which are valid for quiz 1. But for now, we're going to play in user land, and it's essentially interrupts for user processes. So if I try and Control-C my open example or the read-write example, we'll see that it behaves nicely. So if I run it and hit Control-C, whoops. If I run open example and hit Control-C, it stops and I can type back on my terminal again, which is what we expect. But now we notice something kind of odd. What is this? Yeah, so that means that the process exited with this as its exit code, and nowhere in my program, the only thing I return from main is a 0. So the question is, who called exit 130? Not you. So we're going to see what we can do and answer the question why some programs don't die when we hit Control-C. Yeah, so it's basically an interrupt handler. So we're going to see how to do that. So Control-C just sends a signal to your process, which is basically an interrupt, and a signal is literally just a number. And there's just some numbers that you have to look up in a table, or they're given names, and you have to just kind of figure them out. So Control-C sends a signal called sigint. So it's supposed to represent an interrupt from keyboard that the kernel passes on to you, because usually that would have to be dealt with in hardware. And then there's default handlers that you don't have to write. So there's the default handler for interrupt signals that you don't have to write will just exit the process immediately, and it will add 128 to the signal number for its exit code. So if we do a little bit of math, we got returned 130. Well, 130 minus 128, signal interrupt must be signal 2. So let's go ahead and write our own signal handler. So this is basically how you set your own interrupt service routine. So let's go ahead and see an example of that. And here are a list of some of the signals. So 2 is sig init, which is interrupt from keyboard. And there's some signals that are non-standard, but these are the ones you'll probably have to deal with. And there's sig kill, which we saw last lecture, which was like the Uber kill. So that's number 9, and that's terminate immediately. And you can't install a signal handler to interrupt or to kind of handle that signal because it's all done by the kernel. And then remember, your process is ultra dead at that point. Then we see everyone's favorite, signal 11. So that is a memory access violation. That is a seg fault, which kind of begs the question, if it's a signal and I can handle it, so you can actually, a seg fault is not the end of your program. You can catch it and you can keep trucking on if you want. And then the last signal is signal 15. So that's like the nice way to tell a program, hey, you should stop whatever you're doing now, clean up your resources, please shut down. And that's like the nice way to tell a process to please shut down. So that's the default thing to do. All right, let's just see what that looks like. It's a bunch of code that we can gloss over, thankfully. So in our signal example, it's otherwise exactly like our open example. And the only thing new is these register signal functions. So basically, this register signal functions, all it does is register a signal handler to run whenever this process receives the signal. So this signal wants to handle sig int, so control C basically, or sig term, which is like the nice way of saying shut down. Then in register signal, the system call is called sig action. And how that works is you just declare a struct of sig action, and then you would empty it with this to set it to null values. And then you can specify a signal handler, which is just a function, which is something that you can write. And then you just call sig action to say, hey, I want to handle the signal, and this is the function to call. And register signal, this format is something you'd like only ever write once. You'd like look it up on Stack Overflow and then forget you've ever done it again. So in the handle signal, it takes the signal number as the argument, so we can reuse it to see what signal it came from. And here's my amazing handle signal code. So I'm just going to printf, ignoring it, and I'll return. So now if we execute this program, and I hit Control C, I expect it to just keep on trucking. But if I press Control C, it says ignoring signal 2, and then it would have returned. So remember, this is like an interrupt, so you can't control when it triggers or anything. So wherever your process is executing, as soon as a signal comes in, that signal handler is going to run no matter where your program was executed. So it just boots it out and then runs the signal handler code to completion. So it would printf ignoring signal and then go back to whatever the process was executing before, which in this case, before I hit Control C, it was just waiting for me to write output. And we see, good thing we programmed defensively, because the read system call gets an error. And when it prints out the error, it says interrupted system call. So you actually have to retry system calls sometimes because they can get interrupted by signals. So the fix to that is we can write another version of the program that in the while loop, it sees if there's an error, and if there's an error and its error no is equal to this number that you would have to look up that represents an interrupted system call. We know that read didn't return anything bad. That file descriptor is probably actually fine. I just have to retry read, so I just say continue so I can go and issue another read system call. So if I do that now and run signal example 2, that actually retries. Now if I hit Control C, it just says ignoring, but otherwise continues on as normal. And I can say hi, hi, repeats back to me. I can hit Control C again, and this is like your program that just ignored you. Yeah?
Is there a reason why you want to ignore that?
I feel like it.
Can you scroll up a little bit?
Code or
terminal.
terminal?
What if the return code is 4 in your last execute?
4? Oh, this? So that's the code for the interrupted system call. So I just return that at the end. I return error no if I see an error. That's just the number that means the system call got interrupted.
Okay. And one more thing I want to confirm is that handle interrupt function is like the function that's going to be executed before the process being executed.
No, so this handle signal, this gets executed whenever a signal comes in. And it's exactly like an interrupt service routine. So no matter where your program's executing, that handle signal will get called whenever it gets a signal. So every time I hit Control-C, it gets executed. In this case, it just straight up ignores me, right? And because, and the other way to send signals to processes, so this is Control-C sends a signal, but the other way is, because of our violent natures, instead of things being called send signal or something weird, the command's called kill to send a signal. So I can look up what's the process ID of that example that's running by running PID of. It's called signal example 2. So I can get its process ID. Yep.
So is this signal is just like exactly same as the interrupt, right?
Yep.
So it will do something like if I register this kind of handler,
Yep.
it will put this function maybe in the interrupt vector table.
Yeah, the kernel would have something that's like an interrupt vector table for your process. Yep.
Professor, I thought the signal example 2 is terminated, so why is there a...
No, it's still running. It's just
it's another terminal.
oh yeah, so I just opened another terminal up there. So it's still running, it's still happily ignoring me because I'm hitting Control-C, it's not happening, so whoever had that program you can kill with Control-C did something like this.
What
Yeah.
did EINTR mean?
Sorry?
What did EINTR mean? When you check if it equals to that, you will continue.
That's just the error code for an interrupted system call.
Oh, interrupt system call.
Yeah, and I know I can just restart it. So here I got the process ID of what's running in my other terminal, and I can send a signal to it, and we of course do that with the kill command because we are violent people, apparently. So kill, essentially all this program does is do a system call kill. So kill is a system call that sends a signal to a process. So if I kill that, like I really want to end my program, we can see that by default, it'll send signal 15, which is the please shut down. And of course I ignored it too, right? So my process is still happily running, and I ignored it. But if you're writing any kind of good program that behaves normally, kill should actually kill it, and it should clean up all its resources, free whatever it needs to do, and then carry on. Well, we learned last time what's ultra kill? -9, right? So if I do that, it's now dead, and it says killed. Yeah.
Just curious, going back to pipes and all that earlier, could you have run PID of whatever the name was, signal example 2 piped into kill -9 without working?
If it was still running, yeah.
If it was still running.
Yeah, you can kill any process on your machine. And yeah, you guys sadistically made me kill my init process and close out. So you can kill whatever you want. And just to show that that kill is special, hey, what about if I just want to try and ignore kill? Right? Like, I don't want to listen to the kernel. Screw the kernel. If you do that, it says, hey, sig action invalid argument. You're not allowed to ignore kill. Even though it wouldn't run it anyways, it still kind of saves you from shooting yourself in the foot. Yep.
Can you show the register signal code again?
Register signal. Here it is. So it's basically just declaring a struct and then setting it to whatever it represents null values as through that function. And then it just has a field called SA handler, which is a pointer to a function. And that's just the function to run. And then this is a system call that registers that action to it. So you can do more for an action. But for now, for the purposes of this course, we just say what function we want to run when a signal comes in. Okay, so that was fun. So, and this is kind of an example of concurrency too, because our process switches to the interrupt service routine, but it's also not exactly concurrency because it can't switch back and forth again. As soon as it starts running that interrupt service routine, it won't stop until it's done. And we'll see that here's just for reference that you have to account for interrupted system calls sometimes because signals will do that to you. Signals are actually kind of the bane of programming on Linux, and you'll have to use signals in Lab 3 for stuff. So Lab 3 is probably going to be hard because you have to deal with this stuff. So here's just more reference to send signals to processes using their PID. This is just documenting what I showed previously when I got the process ID and tried to kill it. Okay, so here is the more valid stuff. So most operations on your computer are like non-valid. So think if you're the kernel having to deal with hardware changes. Most things would be kind of like the non-blocking nature. So remember when we called wait before, it just blocked until a child died and then it returned and then we handled it. So for the most times, especially if you're dealing with interacting with hardware, there won't be special function calls for hardware that block. They'll be non-blocking. You'll have to check a value or something like that and see if there's a change. So just to kind of illustrate that, we'll turn wait into a non-blocking call. We have to use wait PID with this no hang option, and then it will make it return immediately. So, and that's how wait PID will return a process ID of 0 instead of being an error or the child that died, because now if you just poke it and say, hey, is a child dead? The answer could be no. So if you get a 0 back from that, it means you have a child, but they're not dead yet, right? So if you want to react to changes to a non-blocking call, we can either pull it, so we just keep on trying it, or we could hopefully install an interrupt. And this works at a user level and also at a hardware level. So because we're writing user code, we're just writing C code. We'll see what it's like at a user level. So let's go look at our pull example. So just to illustrate that, so in our main program, we're going to immediately fork, create 2 processes. Who cares about errors? If it's the child, it's just going to sleep for 2 seconds and then exit. So the child process is just going to sit there for 2 seconds and then exit normally. In the parent process, we'll set temporary wait PID to 0, which should mean the child's not dead yet. So we'll just initialize it to 0. And we're going to count how many times we call wait PID. So we just have a while loop that keeps on pulling it, so it keeps on asking, is the child dead, is the child dead, is the child dead, over and over again. And we'll go ahead and count the number of times we make this system call. So if we go ahead and execute that, which is wait pull example, we'll see, oh, yikes. So I called wait PID over 200,000 times. That does not seem like a good idea. Yeah, anyone want to tell me, was that a good idea what I just did, or what's the drawback of that approach? So I just wasted a bunch of time, right? It's just pulling over and over again for over 200,000 times, there is no change. Could anyone think of a better way to pull this without wasting so many calls? Yeah. Without interrupting while still pulling. Yeah, so if I wanted to bring that number down, I could just, if it doesn't work, I'll just sleep for a second or something like that. Then if I do that, call wait, attempt, oh, okay, now it exited. So what's the drawback of doing that now? Yeah. Yeah, I don't know how big of a gap I choose. There's some type of trade-off, right? Which is why we're in engineering. So if I set a number way too big, it's not going to be terribly responsive, right? Because here I could wait up to a second before I actually notice that the child dies. But the smaller I make that wait, the more overhead I'm going to have because most of the calls are going to be useless, right? So having that trade-off between how many times I pull versus how long I wait is one of the trade-offs you have to make. But the better option is to just interrupt. So luckily for us, whenever a child dies, the kernel actually sends you a signal. So we'll go ahead and combine the two things we did, and we'll register the signal called sigchild. Please don't ask me why it's missing an I. We're programmers. We're trying to be efficient as possible. So in this case, it forks, and to show that the signal will actually interrupt us. In the child, we're going to do the same thing: fall asleep for 2 seconds and exit. But in the parent, we're just going to have an infinite loop that sleeps for 9,999 seconds. So the parent's not going to do anything useful. It's just going to sleep pretty much forever. So in our signal handler, we'll check that we're actually getting a sigchild. In this case, I only installed that signal handler, so that should never be true. But otherwise, I handle that signal, and inside our interrupt service routine, I call wait there, and I'm doing the same thing with no hang. And this is just a shortcut, just because I don't want to. When you fork, you'll know the process ID of your child, but I wanted to be lazy here and not save it as a global variable or something. So if I put -1 as the argument, wait PID becomes exactly like wait, so it'll wait for the first child to return. In this case, I only have one child, but so it shouldn't matter what I use. And then if there's an error from that, I'll just print that error. Otherwise, I will print wait, and then I will end this process. So it should die as soon as my child dies. So if I do the interrupt, the main process is asleep, and now it gets interrupted with sigchild because the kernel nicely sends it to me. And then I call wait on it, and it immediately returns, and that's probably the better way to go about things. All right, I'll quickly go over code and then take some questions. So that was polling, this was interrupt. So on a CPU, if you're in kernel land, so these signals are just like interrupts, but for user mode. But if you are the kernel and have to deal with real interrupts, there's kind of 3 different categories you have to consider if you're the kernel, and they're named different things annoyingly. So a true interrupt is triggered by some external hardware, like a keyboard, disk, something like that. And it's handled directly by the kernel, and that's kind of what you did in your computer organization class. Right? The kernel needs to respond super quickly because it needs to react immediately, so it would just take that interrupt. Another interrupt is called a trap, and that is triggered by users. So for example, a system call is an example of a trap. So it's an interrupt that users are allowed to raise that the kernel handles, and that was that SVC instruction, or on some systems it's just called system call. And that's handled by the kernel, which would suspend the calling process, then handle that system call, and then it would resume that process whenever the scheduler feels like it should run. Then the last one is called an exception, triggered by abnormal control flow. So these again are triggered by user processes. They're things like divide by 0, illegal memory accesses, and by default the handler is the kernel, but you are allowed to overwrite this. So with signals, and that's the only way you can do interrupt-like things as a user process. So the process can optionally handle those kinds of traps themselves. So if you really wanted to, you could handle your own seg faults and magically solve them and then keep on executing. And some programs actually trigger seg faults themselves so they can get interrupted, but it's like a whole weird dumb thing. All right, any questions on that or the signals for the child or anything else? So. And this stuff is like, I directly pulled this off, so this is like very valid for a quiz. No hints or anything, right?
So trap is like when you do Control-C?
Yeah. Well, Control C would be, yeah, it's more like an exception kind of, because you're allowed to intercept it. So it's kind of abnormal, but someone's triggering it for you.
Is there an example for the trap?
So trap is just like a system call is a trap. So you trigger it as well as a user process. Yep.
And for interrupt, it's more like you unplug your computer.
Yeah, or like any things the CPU itself has to deal with. And then the kernel would have its own interrupt service routine for dealing with keyboard input or whatever. Yeah.
Any way from the example for the wait function, why is -1?
So that just means an error.
Oh, okay.
Yeah. All right, so wrap it up. We explored basic IPC, that'll serve us well. You even use the open system call in the first lab. So read, write, all good. Redirecting file descriptors is pretty cool. Signals are not so cool, but we have to learn them. They're kind of like interrupts for user process, and the kernel has to handle all three different types of interrupts. So just remember, bowling for you. We're all in this together.